Hey there, geometry class. We're starting a new chapter, chapter 4, which is all about triangle congruence. And I thought I'd start out with a little quote from Auguste Leopold Cruel. And he was a French mathematician living from 1780 to the mid-1800s. And what he said was, "It is indeed wonderful that so simple a figure as the triangle is so inexhaustible in its properties." And I thought that was a really important quote because in this whole chapter and beyond, really, the next chapter and far beyond that, the properties of triangles have just expounded everything that we do in mathematics. And we can spend forever studying them, but really what we need to do here is we're going to focus on two things in this first lecture. We're going to look at congruence and transformation, and then we're going to just talk about how we identify triangles. So here we go. If you're following along in your book, this is sections 4.1 and 4.2. If you have said, you know what, Mr. Rising, your lectures are useless, I don't even care, then the bonus question is, this sweater was worn when my son Kai was born. All right, let's get into it. So let's talk about congruence and transformations. A transformation is can be one of four things. It can be a translation, which is shifting something. And again, this is nothing new, but what might be new is how you represent them in the coordinate plane. So if you're taking notes, this would be a great chance to write down these concepts. You can pause the video. When you add a value to the x-coordinate or the y-coordinate, that is a translation. You're sliding it from one place to another. A reflection can be across the y-axis or across the x-axis. You can flip it up or down or side to side. And there's another one later on, but we're not going to get into that now. And again, you do that by taking the opposite of the x-coordinate if you want to flip over y, or if you want to flip over x, take the opposite of the y-coordinate, like that. A rotation simply means a turn. How you do that is you switch x and y and then take the opposite of one of them. If you switch, if you do the opposite of both, then you do a 180-degree rotation. The last one is called a dilation. It's where you make something bigger or smaller. And that has a scale factor attached to it. And that's what this little k stands for, is you multiply the x-coordinate by k, and you multiply the y-coordinate by k. We're definitely going to spend a lot more time with dilations when we look at triangle similarity in the spring semester. All right, so again, I talked about a dilation having a scale factor. That scale factor, if it's greater than 0 and centered on 0, 0, the origin, it maps it. So again, if this was your original point and you multiplied the x-coordinate and the y-coordinate by k, that would shift it right along this line. Now, we'll get into this a little bit more later on, but I think that's the big thing that you need to remember. Little note here, in a transformation, the original figure is the pre-image, the resulting figure is the image. So let's take a look at this problem here. It says, apply the transformation m, which means multiply the x-coordinate and the y-coordinate by 3, and do that to the polygon with these vertices. Okay? Then it says, name the coordinates of the image points, identify and describe the transformation. And we're back. So my transformation m means to multiply the x-coordinate by 3 and the y-coordinate by 3. So I take each of these 3 points and I multiply the x-coordinate by 3 and the y-coordinate by 3. So the pre-image point D with the coordinate 1, 3, multiply the x by 3, you get 3, multiply the 3 by 3 and you get 9. And so that image point D prime is 3, 9. Do the same thing with the other 2 points. 1 goes to 3, negative 2 goes to negative 6. E prime is 3, negative 6. And F, 3, 0 goes to F prime, 9, comma 0. So identify and describe the transformation. Well, of course, this is a dilation with a scale factor of 3. Each coordinate's getting multiplied by 3 about the origin, or 0, 0. Now, isometries are transformations that preserve congruence, which means the shape is exactly the same. All the angles are the same. all the lengths are the same. That's what a congruent figure is. So a rigid transformation is another name for an isometry. And just as a little side note here, translations, reflections, and rotations are rigid transformations. Dilations with a scale factor other than 1 are not rigid transformations. So here's another problem. What does it say? Determine whether the polygons with the given vertices are congruent. Support your answer by describing a transformation. And then it gives you these points. And let's go to the board right now and do them. So I can hope you can hear me loud and clear. A, 2, -1 is right here. This is point A. B is 3, 0. And C is 2, +3. Now, I like to actually connect the dots to say, oh my gosh, I'm actually looking at a triangle. Look at that gorgeous red triangle. Now, because I can, I'm going to switch to a blue marker, and P is 1, 2. P. Q is 0, 3, which is up here. And R is -3, 2, over 3 up 2. And then when I graph this one, I'm like, oh, wait a minute. Wait, these are the exact same things. The only thing it did was, what do we describe that? Right, rotate 90 degrees counterclockwise about the origin. And I'm back. So what about multiple transformations? Yes, the same thing holds true. If you have multiple rigid transformations tied together, they still maintain congruence. So for example, you could rotate and then translate. You could reflect and then translate, or whatever. You could do multiple transformations. If they're all rigid, they will preserve congruence. So take a look at these little problems. So that's actually everything from section 4.1. We're going to jump into 4.2, and I'm exactly halfway through. I don't want to make it too long for you, but here's a little practice. Try these problems, pause the video, see if you can answer them, and then I'll play along. Okay, classify each angle as acute, obtuse, or right. Well, of course, 1, that is a right angle, 2 is acute, and 3 is obtuse. Now, this is a really good question. If the perimeter of this triangle here is 47, find x and the length of the 3 sides. Well, perimeter means add up the sides. So 47 equals x plus 3 plus 2x plus 6. I have to use my projection voice so you can hear me. Plus 3x plus 8. And if I add up all my x's, 3, 2, and 1, I get 6x. And I add these up, 3 and 6 is 9, plus 8 is 17, equals 47. Of course, you're just jumping out of your seat now thinking, subtract the 17, Mr. Risen, just do it. So I'm going to do it, and you get 6x equals 30. That's supposed to be 30. And you divide by 6, and you know that x equals 5. Have I answered the question? I found x, it equals 5. Now find the lengths. So 5 plus 3 is 8. 15 plus 8 is 23. And 10 plus 6 is 16. Boom! In this section 4.2, you're just getting in the practice of classifying triangles by their side length or their angle measured. So again, a triangle is a polygon with 3 sides. We can look at them in a number of different ways. And just to review, segment AB, BC, and AC are the sides of triangle ABC, and A, B, and C are the vertices or the angles of the triangle. Okay, now, what they want you to do is classify these 4 triangles by their angle measures. And the fact of the matter is, this one what can you say? Well, it's definitely acute because all the angles are less than 90 degrees. How about this one here? Well, it's definitely acute, right? All the angles are less than 90, but it is also, it's acute and equal angular. How do I know that? Well, that's a really good point. I don't know that until it is identified that all three of those are congruent. Just like this first triangle here. It looks to be isosceles, but until I make these sides congruent or these angles congruent, it's not a guarantee. What about this one? I don't know. It could be obtuse, it could be acute, it could be right. Well, the moment I go like this, you know that that is a right triangle. And then this one here as well, if it's unlabeled, then yep, that is an obtuse triangle. So that's how you classify triangles by their angle measure. All right, again, same thing on side length. If it is not clearly or explicitly stated that the triangles have congruent sides, you can't assume that unless you can prove it from some other piece of information. So like here, if I go like this, then yeah, this is equilateral. If I go like this, then you know this is isosceles. And if nothing is the same, then it is scalene. All right, we're at 11.5 minutes. We just have a couple more slides. All right, classify, it's supposed to say triangle FHG by its angle measures. Well, this is trying to get you to look at a picture. FHG is this one right here. If this is 60, then this is 60. And if this is 30, that means this one has to be 60. Oh, so this is an example of an acute. An acute means the largest angle is less than 90 degrees, and it's equiangular. Now, for you smarty pants out there, you're jumping out of your seat saying, well, Mr. Rising, doesn't it also make it equilateral? And it does. But right now, it just says classify it by its angle measure. Now, this one, classify triangle ACD by its side length. Again, let's just practice ACD. Ooh, okay, so we're looking at this one. This side is 18. This side is 5. These two sides have to be the same. So this one is also 15. So this would be an example of a scalene triangle. Any questions there? Okay. I just have 2 more slides for you. Find the side lengths of the equilateral triangle. Well, the moment that they says it's equilateral, then you know all 3 of these have to be the same. So pick 2 and set them equal to each other. I'm going to choose 3y minus 4 and 2y plus 3. Of course, get all my variables on one side, all my constants on the other. So I'm going to add 4 to both sides, and I'm going to subtract 2y from both sides. So now I've got 1y equals 7, and now I can substitute this value into any one of these that I want, because you know what? I know they're all the same. So 2 times 7 is 14 plus 3 is 17. Now, I can double check it. Let's just plug it in here as well. 3 times 7 is 21, minus 4 is 17. So that is also true. Okay, the last problem I want to go over, it says each measure is the side length of an equilateral triangle. Determine how many 7-inch triangles can be formed from a 100-inch piece of steel. So imagine you've got an equilateral and equiangular triangle that the sides are all 7. Well, how many can you form from a 100-inch piece of steel? Well, first of all, think about the perimeter. How much steel is needed to make one of these triangles? Well, perimeter, side plus side plus side. 7 times 3 is 21. Well, if you have 100 inches of steel and it takes 21 inches per triangle, when you divide those, you get 4.76 triangles, which means 4 whole triangles because you can't make a part of a triangle.